Hello, everybody. My name is Ambra Celotto. I'm a second-year PhD student at NTNU, the Norwegian University of Science and Technology in Trondheim. My main supervisor is Professor Berto, and I'm going to present you how we developed, by in-situ studies, a microscale technique for cold bonding aluminium in a focused ion beam microscope. So what I'll be talking to you follows this outline. I'll start from the context, so the reasons why we're doing this, and the approach chosen for doing this, and the instruments and the tools adopted. We will then move into the evolution of the technique, so how we tailored the setup, how we developed the technique, how we characterized it. And then, given the results of the characterization, we were able to optimize the technique. So we will see the modifications, the improvement, and achievements. And then I will sum up what we have learned from that and what we are going to do in the future based on our results. So let's start from the context. So the reason why we are doing this is to investigate and to understand what is happening at the interface between two materials when they are welded at the solid state. And this is made in order to optimize the joint mechanical and electrical properties. We took inspiration from a hip joint, which is a type of joint that has been patented by people from the group. And this process, the hip process, is a solid-state welding technique that involves plastic deformation, the addition of a filler metal, and it's able to couple up to 4 different materials in just one pass. So the in-situ approach was chosen in this study, and this is because it gives the opportunity to check in real time how the process is behaving while it's being done. And in general, it gives very localized information and data on your experiment. But on the other hand, for doing so, one should also downscale the process. So starting from our heap process, which is a very complex one, it was necessary to simplify it. And therefore, we took example from another solid-state welding technique that is called cold pressure welding. This method consists in putting in close contact two metal pieces under a certain load and making them achieving bonding at the room temperature. This method is well known for exploiting two of the bonding mechanisms, of the several bonding mechanisms going on in the heap process, which are pressure and surface expansion. So we will use this technique as main idea and main inspiration for the developing of our new microscale technique. The instrument used in this study is a focused ion beam scanning electron microscope, which, as you can see from the picture, is basically an SEM, a scanning electron microscope, equipped with other several tools, which are, first of all, the electron beam that allows us to image the sample. But the sample can be watched also with another perspective, thanks to the focused ion beam, which is tilted with respect to the electron column. This is a gallium ion beam, and when focused, this allows us also to spatter out material pieces and to mill the sample, basically, in order to obtain some nano or micro structures on the sample. And these new structures that has been created, they can be transferred or moved inside the chamber thanks to the OmniProbe micromanipulator, which it will be important in the following of this presentation. This is equipped with an interchangeable tungsten needle. And then there's the gas injection system that has the several chemical species that can be deposited by chemical vapor deposition for creating gluing or protection layers. Now let's have a look on how the technique has been developed. So The principal aim is the fabrication of a joint between an AA682 towards an AA1070 aluminium alloys. And everything is based on the use of this OmniProbe micromanipulator that, as I said before, is equipped with an interchangeable tungsten needle. This will work both as an actuator, so it will apply the force needed for achieving bonding, and also as a material feeder. How we can feed this material, our aluminium alloy, by replacing its tip. So we will take the tungsten needle, cut its tip, replace it with an aluminium tip, and secure it with a robust ring of platinum deposited by the gas injection system. In this way, we will get this hybrid needle that will feed this material on its tip. In practice, we take a new tungsten needle, we put it in the fib stage together with a piece of filler metal that has been previously mechanically polished. And by using the microscope, by fib milling, we take out from this aluminium wedge a tip shape of aluminium. And in the same way, by fib milling, we truncate the tungsten needle. And by using the micromanipulator, we lift out the aluminium tip and put it in contact with the surface of the tungsten needle. Of course, to secure them together, we have to shave the exceeding part of aluminium, of the aluminium tip. And this shaping procedure takes place in this manner. So we take one side of the aluminium tip, we shave it, we rotate the needle, we add a small rectangle of platinum deposited on the interface, and then we keep on doing like this for the all 360 degrees all around the needle in order to obtain at the end, our hybrid needle. This will be fed in a base metal in order to be bonded with the base metal aluminium alloy. The very preliminary attempt consisted in feeding the filler metal in a groove digged in the base metal, so basically pushing the hybrid needle inside a groove. But in reality, the needle turned out to be very, very sharp, and this didn't create the conditions for achieving the enough shear stresses between the walls of the groove and the sides of the tip. And this led to having no sticking at all between the parts. This made us change the geometry of our setup, and we did it by creating a thicker aluminum tip for the hybrid needle that was meant to be smeared onto the base metal that has no groove at all. So basically this was the expected setup. But in reality, what occurred is that the absence of any groove, any guide for the filler metal to be spread into, led the tip to detach from the tungsten needle. And the tungsten needle actually worked as a punch for this filler metal to be actually spread onto the base metal. And by punching the aluminum tip, the resulting situation was revealing this high plastic deformation of both metal pieces in contact, and the possible bonding interface was identified in this white circle. This region was then cross-sectioned, and by the cross-section, it was visible that these two metal pieces, which are different in microstructure, were in close contact and separated by a bonded interface. So this procedure looks to be promising, but of course had to be made systematical and reproducible. For doing so, we designed a new setup that actually revealed to be the established technique at the end. And this is made by tilting the base metal 45 degrees, so making it perpendicular to the feeding direction, so to the hybrid needle axis, and by drilling a blinded hole in the base metal. As in these simulations here, the filler metal is meant to fill the hole and to create bonding at the interface between the two metals, of course. And because of redepositioning when drilling the hole in the base metal, the hole is expected to be conical. And this is actually a favorable condition for us because this increases the friction forces while the needle tip is advancing inside the hole. So in practice, what turned out to happen, it was something like this. So here the needle is pushed inside the hole. There is a slight misalignment because the base metal is sliding, so this has to be optimized, has to be improved. But one thing, we were actually able to push it with no limits inside the base metal. And then when the needle is retracted, there is no tip anymore sticking on the tungsten needle. And this meant to us that, of course, there was something stronger retaining the filler metal tip inside the hole. And this was actually very likely to be some bonding. So watching from the top, what we can already call our microjoint, we can recognize this rounded filler metal tip that has been stuck into the base metal plate. And by doing a cross-section of this joint, we can see a quite clear bonded interface separating the two metals. And overall, it is possible to notice this quite severe plastic deformation that both materials undergone. In the case of the filler metal, this is recognizable because all the regional porosities that are present in the starting material were closed down. And in the case of the base metal, the depth of the work affected area were increased by the pressure applied. But if we try to compare this microjoint interface with our reference macro scale called pressure welded joint, we notice this white line in the interface that doesn't match the macro scale sample. And by doing EDS analysis, this revealed to be gallium implanted in the interface. This is actually a quite well-known problem when one's talk about aluminium inside a gallium fib. And this because aluminium is very sensitive to gallium. Gallium is able to diffuse quite well along the grain boundaries of aluminium, and this often results in a weakening effect on the aluminium. The gallium is able to weaken the strength up to a factor of 10. So this means that for the sake of our welding, we have to get rid of it. And this is expected to occur when we are drilling the hole in the phase of the preparation of the base metal before the welding. So let's see now the optimized version. The main difference with the previous setup now is that instead of making a blinded hole, we'll drill a through hole. And this is made by having an empty space under the base metal wedge while we are drilling with the fib the hole. This will make the gallium free to evacuate from the bottom. And by using also a lower current for doing this, the general amount of gallium on the bottom of the joint and on the walls of the holes is expected to be reduced. Moreover, another improvement that was done to limit the sliding effect of the base metal while pushing the needle was to change the carbon tape that was originally sticking the base metal to the fib stop with a super glue layer, but which of course, being not conductive, had to be connected with the ground by a carbon tape connection to make it feasible inside the SEM, of course. So looking from the top, the welding experiment looked like this. First of all, the sliding effect of the base metal is heavily reduced. That means a very slight misalignment between the part was detected, and also the formation of the both parts was visible. And once again, when retracting the needle, the filler metal tip is stuck inside the hole. And this to us is quite comparable to a preliminary qualitative tensile test for assessing the bond strength. Once more, by cross-sectioning the microjoint in its middle, we find ourselves in front of something that is quite similar to a conventional V-shaped butt joint, that in this case is just axisymmetric, that in which the deformation of the grains, above all in the base metal, can tell us something about the flow of the metal while the welding was occurring. So by considering that the filler metal is way stronger than the base metal, which is a pure aluminium alloy, the filler metal tip, while it was advancing, was also smearing some material pieces from the walls of the hole and dragging them down towards the bottom and starting to build up material in front of the filler metal tip while it was advancing. So this is why this joint actually has a bottom that was not designed, but this is actually a sign of really, really heavy deformation between the two components. And also, as written here with the arrow, the regional corners of the holes were open up towards the external side. EDS analyses were performed also in this cross-section, and still gallium particles were detected in the interface region. So since we can consider that all the possible precautions against the gallium implantation that can be developed during the fabrication of the samples were actually taken, now we have to distinguish whether this gallium comes from the fabrication of the samples or actually it comes just from the cross-sectioning procedure. This is our open issue to be assessed and solved. Let's have a look now on what we have done in a summary and what we are planning to do. In summary, we can say that first of all, by limiting the degrees of freedom for the filler metal tip while it was being pushed, was able to have a lower probability of premature failure, and this made the method quite reproducible. And the high plastic deformation that was undergone by both metals, above all in the established procedure, made the method also really effective. But on the other hand, we have to admit that the gallium implantation is an issue that cannot be avoided, and there are some lack in our knowledge, for example, the nanoscale bonding mechanism, and of course, maybe the most important one, the bond strength and the mechanical properties of the joint. So future plans. For solving this issue of the gallium implantation, we are considering the employment of a plasma FIP, which exploits the argon ions instead of gallium ions. Then people from the group are working to investigate the bonding mechanisms at the nanoscale by transmission electron microscopy with the TM. And we are working on creating some cantilevers out of the microjoint in this location here to perform bending tests by nano indentation of those. The cantilever is meant to be created with by putting the interface region really close to the root of the cantilever in order to create a tensile stress condition on the interface and to try to test it in a tensile mode. And this will be first done in a macroscopic sample, they're called pressure welded joint, both to act as a trial, but also as a reference for the microscopic one. For this work, I want to acknowledge the contribution of the INSANE project, of NTNU Nalolab, which is a NORB-FAB facility, and of the Research Council of Norway. This is our wonderful Trondheim, and this is me having fun in the lab. Thanks a lot for your attention and your time, and here are my contacts for further questions.